Can you hear that? That's a standing wave. Standing waves have been a well-known physics phenomenon, and our group decided to look further into its importance and the nature in which it serves in the real world. In this project, we have demonstrated the relationship between tension, wave speed, wavelength, linear density, and frequency utilizing a miniature guitar. First, standing waves occur when a wave is confined between two boundaries. Here you can see that the two mediums are at two different lengths, which allows us to know that there are two different tensions occurring. In this clip, you can see and hear the standing wave of our fat string. In this clip, you can see and hear the standing wave of our skinny string. Considering the two mediums and different tensions occurring due to the length, we were able to retrieve the note emitting from their materials. The fat string sounds like a B flat, and the skinny string sounds like an F sharp. With these tones, we Googled their corresponding frequencies. As you can see, the skinny string has a frequency of 185 Hertz, and the fat string has a frequency of 116.54 Hertz, which makes sense due to their tension and density differences.
Due to the varying linear densities, we were able to retrieve frequencies. This helped us understand different wave speeds and their direct relation to the change in frequency, which helped us understand the speed of the wave is affected by tension. Our goal was to find the tension of each string based on a specific frequency presented by the varying linear densities of the medium.
Here you'll see our math calculations for the fat string. Our known values were length, mass, and frequency. We used our formulas: wavelength formula, speed of the wave formula, the linear density formula, and the tension of a string formula. Our final result was that tension was 2.17 times 10 to the negative 6 newtons. Here you can see the calculations for the skinny string. Again, we used our known values for length, mass, and frequency. We also used the same formulas: the wavelength, speed of the wave, linear density, and tension of the string. Here you see that the tension was 1.18 times 10 to the negative 5th newtons. As you can see, these are our quantitative data numbers. The fat string definitely shows a little bit more tension than the skinny string. But because we have no way of confirming these calculations by measurement with a tool, Tristan will now demonstrate the qualitative effect.
The qualitative demonstration of the difference in tension is the effort necessary to stretch the rubber bands into the position that they were put for measuring the frequency.
In conclusion, the linear density of the bands is their greatest differentiating factor because the fatter string emitted a lower frequency sound even though it has a higher tension being applied to it, and the skinny string emitted a higher frequency sound even though there is a lower amount of tension being applied to it.